Okay, this video is for calculus, section 1-2, so second section of chapter 1. Section 1-1, not too bad. Section 2, still review. Everything in chapter 1 is review. This one gets a little bit into some nitty-gritty stuff. If any of this stuff is not really familiar to you, then you need to do reviewing beyond what's in the book. I also recommend that you read section 1-2 in your book. There's a lot in there that's not in these notes. And as we go through, I'm always going to be telling you to read your book. Alright, so a bunch of learning targets here. This video probably won't get to all of these. I can identify domain and range, super duper important, all the way through calculus. I can recognize even and odd functions, super duper important, all the way through calculus. I can identify and find formulas for piecewise functions, a lot of piecewise in calculus, and composition of functions. I'm hoping we get through these two objectives in this video. So what is a function? So you have an input, right, which is your x's and your domain. And for a function, for every input, you have only one output. Okay, so that is what makes it a function. So let's do this. Okay, and then you have an output, which are your y values, which are your range. So this is our first thing, only one output for each input. Functions, the graph of functions passes the vertical line test, if you remember that. Vertical line test, take your graph. I'll do a quadratic. If you put a vertical line through it and it only crosses at one spot, then it's a function. So passes vertical line test. Domain and range, we're going to talk about more when we do these example problems and the ways we want to write domain and range. Okay, so let's look at example 1. Once again, read your book. They have a lot of good stuff on domain and range to help remind you. Identify the domain and range, then sketch the graph of the function. No calculator. So congratulations if you can punch this in your calculator and get the graph. That's great. I don't want you to do that. I want you to do it without a calculator. A lot of these, I want you to be able to picture the graph from memory, but if all else fails, you do a little table of values. So this is the function we're going to graph. The parent function for this is plain old 1 over x. Okay, so if you can picture 1 over x in your head, looks like this. Curve here, undefined when x equals 0, because you cannot have 0 in the bottom of a denominator. Another way to say that is this function has a vertical asymptote at x equals 0. Okay, so the same kind of things are going to happen for this function. So let's first find the vertical asymptote for this because it's helpful for graphing. So a vertical asymptote, to find a vertical asymptote, you take your denominator, set it equal to 0, and solve for x. So x equals 1 is your vertical asymptote. So then I would go to x equals 1 and sketch your vertical asymptote. So the graph will never have a point on this line. Because if x was 1, you'd have 1 minus 1, you'd have 0 in your denominator. Can't have that. Now let's check also before we graph. I like to do this before we graph for a horizontal asymptote. There's not a lot of room here, so I'm going to do this down here. So horizontal asymptote. So there's some rules for this, and what you're looking at is you're looking at the degree of the numerator, and you're comparing it to the degree of the denominator. I'm going to abbreviate that. So if the degree of the numerator is less than the degree of the denominator, then you have a horizontal asymptote at y equals 0. if the degree of the numerator is equal to the degree of the denominator, then you have a horizontal asymptote that is the ratio, I'm just going to write ratio of coefficients. So for example, if you had something like this, degree 2x squared over 3x squared, so the degree, this is my degree, it's 2. Degree is the same, so the horizontal asymptote would be at y equals 2/3. Okay? Example of this, degree of the numerator less than the degree of the denominator, well that would be 1 over x, right? This has a degree of 0, this has a degree of 1. So this would have a horizontal asymptote at y equals 0. Remember, horizontal asymptotes are going to be horizontal lines, so their equation is going to be y equals. And then the last case is where the degree of the numerator, let's see, what do we do? Less than equal than, is greater than the degree of the denominator. No horizontal asymptote. So in our case, degree of this is 0 because this is like having x to the 0, which is equal to 1. So degree of the numerator is less than degree of the denominator. So our horizontal asymptote is y equals 0. So that's the x-axis. So we're going to have a horizontal asymptote here. Okay. Now some points. For some points, I would just do a table of values. And I always like to do these 5 to start. Probably might have to do a few more here. So -2, if I plug x equals -2 in here, let's get rid of this x to the 0 now. I would have y equals -2/3. This would be -1, this would be -2. This would be undefined, right? That's our vertical asymptote. 2 would be 2, 3 would be 1, 4 would be 2/3. Okay, so I did those quickly. You should figure out where I got those. And then you would plot your points. So over -2, down -2/3. I'm just going to put something there. Over -1, down -1. 0, undefined. Okay, over -3 is going to be like this. What's going to happen here is I have a horizontal asymptote here and a vertical asymptote here. So it's going to do this. Approach my asymptotes but never be equal to them. And you know the general shape of 1 over x, so you should know the general shape of this. Okay, 1, so over 2 up 2, so over 2 up 2, over 3 up 1, you know what's happening over here, over 4 up 2/3, so getting close to my asymptotes but never equaling them. Okay? So this is the 1 over x graph shifted 1 to the right, if you remember your translations, 1 to the right. So vertical asymptote of 1 over x is at x equals 0. This is shifted 1 to the right, so my vertical asymptote was at x equals 1. So the parent function for this one, part B, is the square root of x. Right, so you should be able to picture in your head, square root of x does that, right? So let's think about how this is translated. I like this one because that's the easiest. So this is 4 down, and this is 2 to the left. So I'm going to take this graph and I'm going to go down 4, 1, 2, 3, 4, and 2 to the left. Okay, so this point, which was 0, 0, is going to now be -2, -4. But let's do a table of values here. And then see if what I'm thinking here, because I know about translations, is going to be true. By the way, no horizontal asymptote because we don't have a denominator. okay? No vertical asymptote. Okay, so -2, -1, 0, 1, 2. For some reason I threw 6 in there. Y value -4, -3, -2.6. Let's see, wait a minute. 1 was, yeah, -2.3, 2, -2, 6, -1.1. All right, so over -2, down -4. Okay, there's that point I talked about. Over -1, down -3. Over 0, down 2.5. Over 1, down a little more than 2. Over 2, down -2. Over 6, 1, 2, 3, 4, 5, 6, down about 1. Okay, so this is what it's doing, right? Just like we predicted up here. Now what I want to do on both of these graphs also, which I forgot to do over here, I apologize, is talk about domain and range. Okay, so let's do, well, since we just did this graph, let's do domain and range of this one. So for this one, what you need to remember is that we don't want negative square roots. So we want to see or ensure that the square root is always positive, or let's say greater than 0. So we want to solve this for x. So to undo a square root, I would square both sides. So I would have x plus 2 is greater than 0, minus 2 from both sides. So I would say x must be greater than -2. Now, could x be equal to -2? If I put a -2 in here, I'm going to get the square root of 0, which is 0. So x can be equal to -2, which is what we found up here. Okay, so our domain, it can be any x value, -2 or bigger. Notice no part of our graph is over here where x is less than -2. So a couple of ways to write that. I like the interval notation. So x can equal -2, so the bracket means I can be equal to that number. And then I can go to infinity. And then we always use the parenthesis for infinity because it never ends. We can't be equal to infinity. Another way to write this is the domain is x, such that x must be greater than or equal to -2. Okay, so that's our domain. Range, if we think about range, this is where our graph starts. So our y value here is -4. We don't have any y values at -5, -6, -7. We don't have any y values below this line. So range, the smallest y value is -4, and then the y values go up forever, right? We have the y values increasing here. We're going up, 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 up. So you could also write that y such that y is greater than or equal to 4. So squeezing a lot in there. So this is my domain, and this is my range. Okay, let's look at domain and range of this one. Well, we already said that x cannot equal 1, or we have a vertical asymptote at x equals 1. So that means x cannot equal 1. So you can say for this one, domain is x such that x does not equal 1. Or, I still like the set notation, x can be anything smaller than 1. Notice I use the parenthesis here because x cannot equal 1. So that set union this set. That's an infinity, a really bad one. So x can go from -infinity to 1, and then from 1 to +infinity. Okay, so that's my domain. And my range, so think about y values. We said that y is not equal to 0. So range would be y, any y value, but y is not equal to 0. Okay, or you could do the same thing. Negative infinity to 0, union 0 to positive infinity. So that's my range. So these are, recognize that, so when you're graphing, particularly using your graphing calculator, you need to recognize the graph is reasonable. If you know what the parent function looks like, you know this graph should look like the parent function. All important characteristics are vertical asymptotes, horizontal asymptotes, domain, and range. Interpret the characteristics, find them, make sure they make sense, and recognize the graph or calculator failures. We will have times when we will have the calculator will graph something that really is not reasonable. So what I would like you to do is to have a shot at these. And these we're going to do in our calculator. But then see if you can identify domain and range and graph it, or obviously you should be able to graph it because we're doing it in the calculator. And then in the next video, I won't work through it, but I'll have the answers.